So, the axis about which the axis of spin is to turn is known as axis of precession. In the same way, the angular motion of the axis of spin about the axis axis of spin or the precession is known as a precessional angular motion. Then, what is a gyroscopic? This gyroscopic is nothing but a gyroscope is a device for measuring or maintaining the orientation based on the principle of conservation of angular momentum. So, this momentum which is related to the gyroscopic couple. So the momentum is nothing but the displacement. So next, the device is used to measure or maintain the orientation, which is works on the principle of angular moment. The initial axis of rotation is conserved. It consists of spinning mass on the axle. So this is the diagram of a gyroscope, which is to be finding the angular momentum. Since the angular momentum is a vector quantity which is to be represented in the direction of O x dash. So how the gyroscopes are will work. So we are having two types of gyroscopes. One is mechanical and the second one is electronic gyroscopes. These mechanical gyroscopes having the spinning mass mounted on gimbals and free output versus fixed output. The sensors on the axis to detect orientation and the precession. The electronic gyroscope is a correlative vibrational gyroscope. Proof mass feed oscillating current to induce vibration, and vibrating the mass tends to oscillate in the initial plane of reference. So these properties of gyroscopes are basically it is having a two properties, that is the rigidity and precision. So just now we know that the precision and whatever the rigidity, the axis of rotation, that is the spinning axis of the gyro wheel, is tends to remain in a fixed direction in a space if no force is applied to it. Then precision means the axis of the rotation has a tendency to turn at a right angle to the direction of applied force. That is, we are getting in the right hand thumb rule also. Then, what is the history of gyroscopes? In 1817, the Johann Berger created the first no gyroscope, which is called a simply mission. In 1820, the Pearson Simpson Laplace recommended the mission be used as a teaching aid. In 1852, Leon Fourcade coins the name gyroscope when he uses Berger's mission in an experiment involving the Earth rotation. In 1905 to 1908, the first gyroscope for marine navigation was developed by German inventor Hermann Asst.Prof. So this is the history of these gyroscopic. Then, what are the types of gyroscopes we are having till now? So these gyroscopes These gyroscopes are the spinning mass gyro, and optical gyro, and vibrating gyro, gas rate gyro. This is the different applications. Based on the different applications, we are using the different types of gyroscopes which are available in the study. Then the where these gyroscopes are commonly used, since the stability assistance and gyro compass, which is used by ships to find true north and seek minimum potential energy also. And the stability assistance, which are by used in the telescopes and the bicycles also. And inertial guidance system, the guided missiles and measure the angular velocity in inertial reference frame, detect changes to orientation, and combined with accelerometer for 6-axis sensor. The gyroscopic couple. So, for solving or for defining the gyroscopic couple, consider a disk of spin with an angular velocity omega about an axis of the spin OX in anti-clockwise direction when seen from the front. So, this is the angular acceleration what we are finding, angular velocity or angular acceleration what we are finding from the disk. So here we are allotting what we discussed in the precision also the same, but the only the difference it is the axis of precision and angle of precision or a plane of precision that we need to find out. Why? Because the couple is nothing but the momentum. So we have to find out the moment of inertia that is to be applied in the or in finding the momentum of any gyroscopic couple. So consider a disk of spinning with an angular velocity omega, which is of angular velocity omega radians per second about an axis of spin OX in anticlockwise direction. So, since the plane in which the disk is rotating is parallel to the plane YOZ, which is called plane of spinning. YOZ, which is we can see in the diagram, that is YOZ is a plane of a spin, and there that is called the plane of spinning, and the plane XOZ is a horizontal plane, and the axis of spin rotates in plane parallel to the horizontal plane about an axis of OY. So we can say, in other words, the axis of spin is said to be rotating or processing about an axis OY. In other words, also the axis of spin is said to be rotating or crossing about an axis OY, which is perpendicular to both the axis OX and OZ. So the axis of this active gyroscopic couple, which is available in the OY, this we are creating the perpendicular direction to the both axis OX and OZ. So since here OX, OY and OZ are mutually perpendicular to each other. So OX and OY and OZ, these are the mutually perpendicular axes. So these axes may be which are rotating at the angular velocity, that is the precision angular velocity, that is omega p. So this horizontal plane xoz is called the plane of precision and OY is the axis of precision. In the diagram, this OY is the axis of precision and OX is the XOZ is the plane of precision. So we have to aware that the axis of precision is is always perpendicular to the plane of precision, that is XOZ. Let I be the mass moment of inertia of the disk about OX and omega be the angular velocity of the disk. So the angular momentum of the disk, that is I omega. Since you know that angular momentum is a vector quantity, therefore it may be represented by the vector OX dash, that is we are representing in the active gyroscopic couple figure, that is B. So there, that is from X to X dash, it is making a couple or the vector, and O X dash and O X, we both are the contents of plane of spin. The axis of spin OX is also rotating anticlockwise when seen from the top about the axis OY. Let the axis OX is turned in the plane XOZ through a small angle delta theta to the position OX dash in the time intervals of delta t. Assuming that the angular velocity omega to be constant, the angular momentum will now be by a vector O x dash. So with that we will get it the change of angular momentum. This change in angular momentum is O x dash minus, that is the change, that is original to change. So OX dash minus the original is OX. The result of the vector. So these difference may be getting through this x dash. So x dash is equals to the content of the, it looks like a right angle triangle. So x dash bar, that is vector representation, that is arrow symbol will represent the uh, vector quantity. So O x dash, sorry, x dash vector is equals to OX vector into what is the change, that is angle of change, that is delta theta. We know that OX is nothing but the vector of OX is nothing but the I omega into delta. So the rate of change of angular momentum, that is the rate of change of means we get it, the changing is in the only content, the time representation. So since the rate of change of angular momentum will result in the application of a couple to the disk. So change in the momentum is a couple. So the couple will be called it as I omega into delta theta by delta t. This change will finally go for resulting the precision. So the precision formula will be I omega into omega p. So we always remember that the precision is nothing but the omega p, angular velocity of the precision, that is omega p. You know the formula delta, sorry, d theta by dt, and as you know the rate of change of angular momentum, that is I omega delta theta by dt. So I omega up to I omega, that is an angular momentum for the change in the time, that is omega p. So omega p is the angular velocity of precision of this according to the direction of O. Then coming to a problem based on the formulae what we have discussed now. Consider a problem that is a uniform disk of diameter 300 mm and which mass 5 kg is mounted on one end of an arm of like the 600 mm, and the other end of the arm is free to rotate in universal bearing. If the disk rotates about the speed of 300 rpm clockwise, looking from front. So we derive for angular momentum or angular velocity of this. When we see from the front, it looks like in the rotating in the anti-clockwise. So, but here we are getting the information that is looking from the front, the disk is rotating in the clockwise direction. So, uh, whatever the direction that we are giving in the question, that we need to follow for solving. With what speed will it process or process about the vertical axis? The process means the what at what with what speed will it precise about the vertical axis. So at what speed, or we need to find out the speed which is better for the precision of a rotation of the spinning axis. So as per the data, the diameter of the disk, that is a small disk, that is 300 mm, and the mass m is equals to 5 kg, and arm length is m is equals to 600 mm. So n is equals to 300 rpm, or omega is equals to 2 pi n by 60, that is angular velocity and its speed 2 pi n by 60. N is nothing but the speed of that is which is rotating 300. So with that we are getting all the values by converting mm to meters. So that is for SI units also. We know that mass moment of inertia of a disk, which is about an axis through the center of gravity and perpendicular to the planes of disk. That is I, that is mass moment of inertia, I is equals to mr square by 2. So we know m5 r radius and square by 2. So with that 0.056 kg meter square. And the couple. So couple formula we need to note it down, MAL or MGL. That is weight. That is weight or a force into distance. That is nothing but a moment. A force into distance is called a moment. So in the same way, that is a couple. P is equals to MGL. It is mass G 9.81, length what is again 0.6. That is 29.43 Newton. So let what is the speed of precision? That is omega p. We know the formula, that is d theta by dt, but we have to find out the angle of the precision. And we know that the couple is equals to I omega into omega. We know the omega value from 2 pi n by 60 and I mass moment of inertia mr square by 2 and omega p that is the speed he is asking about with what speed will it precess that means precision speed you need to find it. So precision speed is nothing but from the precisional velocity only we can get it. So precisional velocity angular velocity is omega p that is speed of precision. We need to find out that. So by getting the entire data from the solving omega p is equals to 16 radians per second. So this is the final speed. So uh, we can directly get it the normal speed that is n also from here. We know omega is nothing but 2 pi n by 60. So we have to find out is that speed is nothing but the angular speed. Is it okay or normal speed? Okay, both are good for results. Okay, from omega p only we can get it directly np. Okay, then and what are the effects? What are the things? The effect of gyroscopic couple on what are the elements means. Mainly the gyroscopic couple is depending will affect on the it will affect on the aeroplane, ship, four-wheeler, okay, and it is a bike or a two-wheeler what we are doing in the turnings. So here now we are discussing the effect of gyroscopic couple on a aeroplanes. The views of the where we can see that here the views of the front and top views of aeroplane. So the gyroscopic couple is created by the engine propeller or what is the uh, wheel or wings which are having in the front or backward. So let the engine or a propeller rotates in the clockwise direction when we see from the rear or tail end and the aeroplane takes it on to left. So we have to calculate the gyroscopic couple while we are traveling in the direction of turning only. So these will be go for in the major drastic. This will result in the drastic. So let us consider the let omega be the angular velocity of an engine and m is the mass of the engine and the propeller and k is the radius of gyration in meters and m is I is the mass moment inertia of an engine and propeller. So here we are considering the engine and the propeller both are same. So the entire mass of the engine. So actually this propeller and the engine are both are connected to a single shaft. So the entire quantity will be considered as a one unit. The engine and the propeller are considered for total mass. So which is to be in kg meter square also. Basically, we know mass moment of mk square, radius of gyration into mass. V is the linear velocity of aeroplane. We can make it as an angular velocity by using a formula that is V by R. Omega is equals to V by R. So the gyroscopic couple which is acting on a we can get it the formula from the gyroscopic couple, that is the couple is equals to I omega p. For any model or for any vehicle or for any component, the gyroscopic couple is acting is always be more or less same formula, that is couple is equals to I omega p. So during the different types of turnings, that is left turn and right turn, and how the propeller will be rotated, or how the wings is to be operated. Okay, these are the things we are going to discuss. Before taking the left turn, see, an aeroplane before taking the left turn, the angular momentum vector is represented by OX. So the angular three, here also we are having the three axes of spin, that is OX and OY and OZ. These three are mutually perpendicular, and the axis of spin is always be OX, and axis of precession be OY, and axis of active gyroscopic couple is always OZ. So, coming to the point, when the aeroplane is taking to be of left turn, when it is takes place in the left turn, the gyroscopic couple will changes the direction of angular momentum vector from OX to OX dash. This is the direction of representation. So this vector is always be the same, that is x dash. And this in the limit that represents the change of uh, represents the change of angular momentum, or the active gyroscopic couple which is perpendicular to OX. Thus, the plane of axis of active gyroscopic couple is XOY will always be perpendicular to X dash. So whenever the left hand turning, what we are getting the we can find out the direction of active gyroscopic couple is in the clockwise direction. For left-hand turning, the active gyroscopic couple on the aeroplane is in the axis of OZ, which will be clockwise. So we can see in the diagram the direction of axis of spin and the axis of direction of gyroscopic couple on the aeroplane, that is OZ. The reactive gyroscopic couple, which are of equally magnitude of the active gyroscopic couple, will also be act in the direction of the respective OZ. So the OZ rotating in the clockwise, the reactive force, the reactive gyroscopic couple will rotate in the opposite direction, and the effect of this couple is therefore to raise the nose and dip the tail of the aeroplane. So, what is a nose and what is a tail? So, if you see in the diagram from the top view, you can see the propeller pointed at its nose. Okay, in the diagram itself, it has shown, and the direction of wheel and the tail. Tail is nothing but the ending one. So here also we represented the. So for taking the left hand turn. So before taking the left turn, so whenever the flight or the aeroplane is taking the left turn, the couple or the effect of couple is to be act in the opposite direction or anti-clockwise direction. That will result in raise the nose and dip the tail. So for taking the left turn, the engine or the front portion of the aeroplane is to be raised, and at the same time the back portion of the aeroplane is to be raised. So this is the main thing. Whenever the aeroplane taking the right turn, so with the same similar consideration for taking the right turn means we have to dip the nose and raise the tail. So this is the main difference. For left turn, raise the nose. For right turn, raise the tail. So this is the main difference we are having. So we have to remember this for solving the problems also. When the engine or a propeller rotates in anti-clockwise direction, when viewed from the rear or rectile, when it is taken in the left hand, the effect of reactive gyroscopic will be done to the nose and raise the tail. So actually we are taking the propeller when we see from the tail, the propeller is rotating in the clockwise direction. But this case, while taking the left turn means the raise the nose and dip the tail. For right turn, dip the nose and raise the tail. In the same way, for a note of that is the propeller is rotating in the anti-clockwise direction when we view from the tail end. So previously the propeller is rotating in the clockwise direction. Now the propeller is rotating in the anti-clockwise direction. So further we can change up uh, the portion or the ends or the aeroplane taking it left turn means the reactive couple or reactive gyroscopic couple will be done to the dip the nose and the raise the tail. So based on the direction of rotation of the propeller, we have to address the conditions like this. In the same way, when a propeller rotates in clockwise direction when viewed from the front, and the aeroplane takes to take a left turn, then the effect of reactive gyroscopic couple will be raising the tail and hit the nose. So from front view, whether it is a clockwise from sorry from front, that means from nose, it is taking the or it is rotating in the clockwise means from tail it will show that it is rotating in the anti-clockwise. So no need to change up the results also. So both the results same. Okay, from nose or tail. Then when the aeroplane takes the right turn under the similar considerations as mentioned in the above, the effect of the reactive gyroscopic couple will be to raise the nose and dip the tail of an aeroplane. So with that, the effect of gyroscopic couple on an aeroplane is to be finalized. And in the next video, we discuss about the effect of gyroscopic couple on a naval ship. That the topic we will discuss in the next video.